Hi everybody. Today we're going to be going through two sections in the textbook. Section 4.3, which is about using the definition of rational numbers and doing some proofs with that definition. You'll find the flavor of these proofs is very much like the ones where we were using the definition of even and odd. You just suppose you've got a particular but arbitrary element of the set under consideration such that, and then whatever hypotheses are there, and then you see how the definition converts that into something that maybe you can use. Usually the definition turns an abstract statement into something that's concrete, and you can do algebra with it or something. Then at the very end of these proofs, you'll use the definition a second time to kind of revert back to the abstract phrasing. But well, we'll see examples of that. So 4.3 is about rational numbers, and 4.4 is about divisibility. Those two topics, those two definitions are going to give us some nice examples of proofs. They're a little bit tougher than the even and odd type things, but not a whole lot. So we're taking sort of a gradual approach to getting you to be facile with writing proofs. So first of all, let's get rolling then. The definition of rational. Let's start by thinking about we've got a real number, call it x, is rational well, it's an if and only if condition, so this is the typical of all definitions, that they're if and only if statements, because, well, like I just sort of sketched, you're going to need to use the definition in two ways. One, to convert from abstract terminology, like saying x is rational, to, well, what's going to go after here is something concrete. And a second time where you go from the concrete back to the abstract. So what is the definition of a rational number? It's just that it's a fraction. So we say x is equal to a over b for some integers, a and b. And there's an extra proviso that we need on here, which is probably obvious to anybody who's been through a basic algebra class, or even maybe in grade school you learn this. You know how you can't divide by zero? Right? B there can't be zero. A could be zero. So for instance, if a was 0 and b was anything else, we'd have 0 over something, and would show that x was a rational number. So that's writing it out as a sentence. I prefer actually to say it in math notation. The set of rational numbers here is denoted with a Blackboard bold Q. I think that Q stands for quotients, and anyway, you couldn't use R for rationals because reals already have that in use. So x is a rational number. The left side of this if and only if then is expressible like so. X is an element of the rationals. X is in Q. The if and only if becomes that double-headed arrow. And then the rest of this stuff is pretty much okay, except for when you're writing in language, sometimes quantifiers come after the statement. When you're writing in math, you should stick them up front. So we should say there exists a and b in the integers. And what do we need from a and b? That their fraction, a over b, is equal to x. And also that thing about b not being 0. So that's a pretty good, really formalized definition of what it means for a thing to be a rational number. Let's remind you of a pragmatic test. If you've actually got a number like staring at you on your calculator, you can tell whether it's rational or not. Rational numbers have sort of a nice pattern in their decimals, in the things after the decimal point. There's one of two things can happen. Either they have a terminating spot, the decimals go to some point and then it ends and there's no more numbers after that, in which case we just say they're terminating. Or the other thing that can happen is they get a repeating pattern. So I probably should have brought a calculator with me, but there's plenty of numbers that you know for sure are rational because they're written as fractions. The question is sometimes you'll get a number that's written not as a fraction, but actually I'm just going to kill the definition too while we're at it. I just want to concentrate on this idea that the decimal representations, I didn't say that. Oh, wow, this sentence is incomplete. That's my problem. Rational numbers either terminate or have a repeating pattern after the decimal point. That's probably what I should have said. So let's do a couple of examples of that. If you, for instance, take 1/5 as a decimal, that's 0.2. And you're done. Now, one way to think about terminating is that it's got zeros from there on out to infinity. There's zeros in the the hundredths place, the thousandths place, the 10,000ths, etc. And you can think of that termination as being a repeating pattern. It's a repeating pattern of zeros forever. So 1/5 is that. 1/7 is probably my favorite example of a number that's got a repeating pattern because it's kind of a long one. I realized I just needed to go get a calculator to show you this. So I'm going to put in 1 divided by 7 and see if I can arrange to show this to the camera effectively. And get some light on the screen and hit go. Are you able to see that number? Well, all right, fine. It's a little hard to see. Let me copy for you what's actually on the screen of the calculator right now. It says 142857. Wait, 142857, and then 1429. And it looks like there's not really a pattern, but what's going on is this digit right here, that's been rounded up. So it's really an 8 with something that's bigger than 0.5 after it. So what's really going on with this, if I just erase, is we've got another copy of this pattern, 142857. And then there's another 1428. It keeps going forever. And I know people have seen this notation for it. What you do is draw a bar over the sequence of digits that repeats itself. And then that's understood to mean that pattern repeats forever and ever. So we don't need this stuff. 142857 is the pattern you get, this repeating pattern that you get in the decimal points, or after the decimal point, from 1/7. So I guess I'm trying to convince you that this works for every rational number. If you write one number over another, you're going to get either termination, which you can think of as a whole bunch of zeros repeating, or a true pattern that repeats over and over again. And if it doesn't have such a pattern, then it's not rational. For instance, pi is 3.1415928. Oh, my memory fails me. That's as far as I've always remembered it too. 1592. Oh, I've remembered it wrong too. 2654. Do you see any patterns so far? I don't. But you know what? The pattern that happens here could be of any length. There could be a pattern of 1,000,000 digits, and after 1,000,000 digits, we start repeating that same sequence of 1,000,000 digits again. Or it could be, 10 to the 40th power digits, and then that number, after that number of digits, you'd see a repeat of those same first 10 to the 40th power digits. So just noticing that I've got like 9 or 10 digits and there doesn't seem to be a pattern, that's really not good enough. But we know, actually it's been proven, that pi does not have any repeating pattern in its decimals. Pi is worse than irrational. It's a kind of number that's called transcendental. Let me give you another example of something that's not rational. Square root of 2 is really famously not rational. This was known back in the ancient Greek world. One of the followers of Pythagoras was actually, it's argued what crime he committed, but one version of it is he showed him that square root of 2 was not a rational number. And since their entire cult belief was that, numbers made up the entire fabric of reality and rational numbers were good, it was like this guy was saying something irreligious. So when he said root 2 was irrational, they threw him off a boat. Yeah. At least that's one version of the story. I've also heard it told that he may have given up some other secret. They viewed certain mathematical truths as sort of inner knowledge of the cult, and so they didn't want to let people know about it. Where was I? Taking the square root of 2. Yeah, the decimals that we can see anyway are 1.414213.562. I don't see a pattern yet. As I've remarked with pi, that's not enough to not see it. That just means maybe the pattern is longer than I've got accuracy in my calculator. But it is also something that we can prove is not a rational number. So these guys, rational. They either terminate or repeat. These things are in Q. And these two are examples of things that are not in Q. Don't get the idea that this is it. It's not just pi and root 2. There's actually more things that are irrational than there are things that are rational. They're both infinite collections, but that's a bigger infinity than that is, which is fun business hopefully we'll get to near the end of class. Okay, so let's just see one thing about how I know that if I do have I want to point out there's two issues to deal with. There's the idea of if it's repeating, that implies it's rational. And then there's the issue of if it's rational, it should be repeating. That is, the connection between the repetitive nature of the decimal expansion and rationality is an if and only if thing. Well, I want to sort of indicate at least why both of those are the case. So let's do the first one first. I'm just going to show you this by example. Suppose I have the number 0.123, etc., right? So it repeats. It's got the repeating pattern. I should have just drawn the overline here, right? But I wanted to let you sort of see the flow of its digits. Let's call that x. I'm going to multiply x by 1,000 because this period is, the repeating thing is 3 digits long. So what is 1,000 times x? Well, it is 123.123.123, and dot, dot, dot. So look what happens if you subtract these. If you take 1000x minus x, I think I can figure that one out straight up. That's 999 x's. It'll be, well, if I'm subtracting this taking this number and subtracting that one, all the junk after the decimal point is identical, right? So that's just going to be 123. And so I have just deduced that x is this fraction, 123 over 999. That's an example of a fraction that's not in lowest terms. You can tell because if you add up these digits, you get 6. So that's divisible by 3 because 6 is divisible by 3. Add up these digits, you get 27, also divisible by 3, actually divisible by 9. But that's enough. You know there's at least a common factor of 3 between them. So this should be 41 over 333. I believe that's in lowest terms. It has to be because 41 is a prime number. I recognize that. Okay. So anyway, the point is, if you've got a repeating pattern of a given length, you can deduce that the number is rational. And you could run through similar algebra on any repeating pattern. To go the other way, to say that rational numbers have to give you repeating patterns, it suffices, I think, to think about how the process of long division works. So let's do like 7 divided into 3, just as an example. So I'm trying to figure out the decimal value of 3/7. Remember doing division where you had stuff after the decimal point? The problem is that 7 doesn't go into 3, so you get a 0 there. And here's where the decimal point comes in. You multiply back and you get 0 and you subtract, and that's a 3. But we sort of now think of it as a 30. 7 goes into 30 4 times. 4 times 7 is 28. You subtract and you get 2. Does 7 go into 2? Nah. But if we move into the next column and make it a 20, 7 does go into 20, it goes in twice. Yeah. I was about to run out of space, so I went and recopied the thing near the top of the board. Hopefully this will give us enough room to see what happens. Let's see, we already did this. 7 into 20 went in twice, and so when you multiply back, 2 times 7 is 14. And subtracting, we get a 6. 7 doesn't go into 6, but it does go into 60 8 times. 8 times 7 is 56. So we'll subtract and get 4. No, 7 doesn't go into 4, but it does go into 40. It goes 7 times. Right? No, it doesn't. 40 goes 5 times. What was I thinking? I don't know. 5 times 7, 35. Subtract, you get a 5. Does 7 go into 5? Of course not, but it goes into 50. There's where the 7 times comes in. I should cross my 7s. 7 times 7 is 49. You get a 1. 7 doesn't go into 1, but it goes into 10, and it goes in once. Multiply back, 7, you get a 3. Now something weird happens. Now that I got a 3, why did I stop just now when I got a 3? Well, isn't that something we had before? In fact, wait a minute. We had it even before that. So what's going to happen for the rest of the division process? It's going to look like a copy of all this work. And then another copy of all this work. There's just going to be chunks of this thing repeating itself down forever. Once you get back to a repetition, once you get back to some particular digit that you've seen before, like the 3 and the 3, you're going to, well, I guess I should do this once and then you'll see where it goes from there. But my prediction is the next digit is going to be a 4. That's a terrible, I was trying to make a dashed 4, so I was like, I'm not really writing it in, but that's what's going to happen. Because 7 doesn't go into 3, so we have to go into one more decimal point. We have 30, and 7 goes into 30 4 times. Sure enough, a copy of that 4 right there. And then we multiply back, and we get 28. And you see, it's like we're stuck in a loop. We're running through this work again. And the next thing is going to be a 20, and 14 will be how many 7s go into it. And you get the idea? So the fact that the process for doing long division to produce the decimal expansion, the fact that this process is sort of mechanical means that if you ever get back to your initial point, you're going to just fall into a loop of repeating the same thing. In other words, get a repeating pattern. So I was trying to justify that. Maybe I took a little too long on that, but rational implies repeating, and repeating implies rational. Those are connected. All right, so let's do some arguing with this. First statement we're going to prove is that every integer is rational. This is almost too easy because it just kind of falls out. What do you do to prove that an integer is rational? Well, like before, you're going to start by saying, suppose I have a particular but arbitrarily chosen integer. Oh, that is not a good marker. Let's try another one. Oh man, I'm having bad luck. It's cool, I went to Target and got a fresh box. Here we go. Suppose x is a particular but arbitrary integer. I'm gonna start dropping all that particular but arbitrary stuff and just say, suppose x is an integer. Well, x is the same thing as x over 1, isn't it? Because dividing by 1 doesn't really do anything. But this now looks like an integer over an integer. That should probably be done as displayed math. X equals x over 1. And then you say something like, since x and 1 are integers, we should probably put the serifs on that 1 so it looks like it's not an L or something. Since x and 1 are integers, and 1 is not equal to 0, certainly, it follows that x satisfies the definition of a rational number. Which is a kind of a long-winded way of saying this thing. I'm supposed to color that box in. If you were less formal and just trying to tell somebody that every integer is a rational number, you'd say, dude, you can always write it as itself over 1. Wouldn't that be enough to convince somebody that that's right? You can think of a whole number as a fraction with the denominator being 1. There are 4 different proofs we could do next, which are all very much the same, and they're the closure statements for the rationals. I'm going to pick on the sum, but there's a proof like this for multiplying, for dividing, for subtracting, any operation with rational numbers. If you have rational numbers in the operation, you're going to get rational numbers out of the operation. Well, that's not true if you use rational numbers in exponents, but multiplying and dividing, adding and subtracting. What I'm saying is there are closure properties of the rational numbers, which I'm just going to abbreviate by saying Q. And notice I'm not saying closure axioms. These are not going to be axioms. I'm going to just emphasize that point. They're not axioms because it's possible to prove them. If you can provide an argument for the thing, there's no need to relegate it to the world of axioms. We can prove them using the closure axioms for the integers, because the rationals are defined in terms of the integers, and so we use that. But the idea, I guess that's a end of the parenthesis. The idea is that, well, the statements I want to say will look like this. The rationals are closed under addition. The rationals are closed under multiplication. Let's say them all at once. Rational numbers are closed under adding, subtracting, multiplying, and dividing. Kind of using the old school ways of writing, multiplying, and dividing to here. But anyway, that's fine. If I want to say these statements more formally, let me do the one I was intending to prove for you, the addition. I would say something like this: for all x, y. Let's just take them as real numbers at first, but x being a rational number and y being a rational number, those two things imply that the sum, x plus y, is a rational number. In other words, to say it informally, even less formally than I did up front, if you add two fractions, you're going to get a fraction. Right. How would a proof of this statement go? Well, it's generalizing from the generic particular again. So we're going to suppose we have two particular but arbitrarily chosen things satisfying our hypotheses, and their only hypothesis is that they're rational numbers. So, what was I calling them, x and y? Let's suppose x and y are rational. I should make a point about language here, because sometimes I think it's confusing at first. You don't have to say rational numbers. You can just say rational. People understand that you mean a set of rational numbers. So suppose x and y are rational. That's our first boilerplate sentence. But now we're going to use our definition. This is always the second step you take. You suppose they're rational, well, use that fact. Use that they're rational. Since x is rational, there are integers, a numerator and a denominator, right? I'm just going to call them a and b. Such that x is equal to a over b. Oh, and b is non-zero, right? Remember that piece, because you always need that piece. The definition of rationality had two pieces, that you could write the number as that fraction and the bottom wasn't zero. Similarly, I'm just going to say similarly because it's the same train of logic, y is equal to, say, c over d, and d will be non-zero. I've left something out here, but I think a reasonable person would interpret it this way. When I say similarly, and this was saying there were integers a and b, do you get the sense that c and d should be treated as integers? Look, if that's an issue, let's be more clear about it then. So in a line that says where c and d are integers, and d is non-zero. Okay, but really the upshot is x is a fraction, y is a fraction. How do you add up two fractions? Because I'm going to use substitution and say x can be replaced with a over b, and y can be replaced with c over d. I'm debating whether I should do it the wrong way and see if, but since there's nobody actually present right now to yell at me and stop me, if I did it the wrong way, it wouldn't be as funny. It's funnier if I do it the wrong way and then somebody in class yells and says, hey, you're screwing up. What is the right way? When you have two fractions, you have to find a common denominator, and these guys have different denominators, so it's hard to do. What's the greatest common denominator, or the GCD for b and d? They're letters, how could I know? But the truth of the situation is you don't have to find the best common denominator, that lowest common denominator, but rather a common denominator. And the product of these denominators will always work. So what I'm going to do is multiply the first fraction by d in the top and the bottom. So we'll have a d over b d. And the second one I'm going to multiply in the top and the bottom by b. So we'll have cb over bd. Now they have the same denominator and you can combine them. So you have bd downstairs and ad plus bc upstairs. Well, that should be exciting. That final thing there actually is what tells us that x plus y is a rational number. But we want to be careful. Let's sort of dot our I's and cross our T's. I'm just going to continue from the top here. I'm going to notice that since AD plus BC, that's the numerator, and BD are integers, why, you ask? Why do I know they're integers? Because this is a product of integers with a sum. When we multiply integers, we get an integer. When we add integers, we get an integer. That's a combination of the closure axioms. And BD is just the closure axiom under multiplication. And also, there's a little fact from algebra that you probably have forgotten, but it also follows that BD can't be 0. The reason for that is the only way you get 0 out of multiplying two things is if one of the things is 0. I'm saying it informally. There's a formal name for that. It's called the zero product property. If you get 0 as a product, then one of the terms was 0. Let's just abbreviate property like that. So what's our takeaway from this? We've written x plus y as a fraction with something non-zero in the bottom, and both the top and the bottom are integers. So the final conclusion is thus x plus y is rational. I'm going to get rid of this stuff we don't need anymore, because I really, it's very fulfilling at the end of one of these arguments. You go, I get to draw my box and color it in. Or if you like, you can write QED there. Yay. Okay, so that's as far as we'll go with rational numbers. There's other proofs that we can do here, but I want to leave some of them for you to do. Like I just did closure under adding. Closure under multiplying is actually an easier argument. Closure under dividing is also pretty easy. Subtracting more or less looks like this one, except wherever there was a plus sign here, there'd be a minus sign. So those are all proofs that you should, or what you will be asked to do as practice in the worksheet. So let's push on to 4.4, which is about divisibility. I think we ran into divisibility back in chapter 1, but let me sort of hammer down some of those ideas we saw back then. There's a symbol that goes in between two numbers. It's called a relation symbol when one of them divides the other evenly. So you write D, a vertical bar, and N. So that, I'm just putting quotes around it to say that whole little bit means that D divides N with no remainder. Just contrast for a second what it means to say, like, for instance, 3 divides 9 versus 3 divided by 9. They're very different. 3 divided by 9 is a number, right? In fact, you can see they have a 3 in common between numerator and denominator. That's 1/3. What's this? This is asking a question, not proposing a numerical answer, but asking, is it true that 3 divides evenly into 9? Is it? Well, yes, it is. So this thing here is true. You see how true is really rather different from 1/3? The vertical bar, and those things are, typographically quite similar. If you're in an italic font, you might not be able to tell the difference between the slanty bar and the straight up bar. Usually we don't use italic fonts for those symbols, so this guy should generally be vertical. Yeah, all right. So there's a lot of synonyms for this. You can say N is a multiple of D. You can see D is a factor of N. I'm going to, actually, you know what, I'm going to punt a little bit and show you this in the book, because I don't want to write them all down. There's a lot of different ways to say one number divides another. Yeah. See if I can do this without crashing anything. That is, what page is that? 190 in the book. There's this blue box in the middle of the page with all these different ways of saying that one number divides into the other. N is divisible by D, N is a multiple of D, D is a factor of N, D is a divisor of N, or simply D divides N. But the notation D vertical bar N means all of those. Just got to watch out if you're using the one that says something's a multiple of the other, then D and N's roles are reversed. So what's the definition of that? My notes go to the floor. Had to drop something in the course of all that. D divides N if and only if there is an integer such that N looks like D times that integer. Now, if you think about this in one way, D divides N is the same thing. Let's say it's equivalent to saying that n over d is an integer, which is fine. But if you write something like that down, if you do division with numbers, how do you know that it's an integer? Because you're looking at something like the fraction n over d. It looks like it's a rational number, yeah? So we're counting on this, not being the case, that in fact that's not just a rational number, it's an integer. That's what we want to be true. And that is why this definition doesn't use division. Because if I wrote n over d equals k, you'd be like, well, that doesn't necessarily mean anything. Well, actually it would if you specified that k had to be an integer. But by introducing division, you at least cast this little doubt that you might be dealing with rational numbers rather than integers. But you can say the same thing like that with just multiplication. And so you don't have that doubt anymore about whether you're in rational numbers or not. It's actually very clever to use the strictly multiplying to get at the idea of divisibility. When you're in this sort of situation, you remember when we talked about even and odd numbers, I told you the k that exists would be called the witness. Like, I don't know, 7 is a witness that 14 is an even number. Well, k is also called a witness in this thing. The existence of k is the idea. So if you have a particular thing in mind, you have to say, what's k? So let's do a little table of d and n and the witness. Suppose I had d was 2 and n was 14. You have to ask yourself, 14 is 2 times what? 7. So 7 is the witness. If I had 3 and 24, then 8 is the witness. If I had 5 and 45, then 9 is the witness. But anytime that one number divides into another number, you have a witness. Right? For instance, 3 divides evenly into 111. I know that because 111, the digits add up to 3. What is the witness now? I think it's 37. Let's see, 90 and 21. Yeah, that's right. 37 is the witness. So to find the witness, normally you just actually do the division. And what about if there is no witness? Suppose I said 3 and 16 are the numbers. Well, 16 over 3 is 5.333. Well, that's not an integer, so he's not a witness. And in fact, there is no witness for this because it's not true. So that brings up an issue. How do you say that some number doesn't divide another number? The notation for this sort of thing is a crossed out version of the vertical bar. You'd say 3 vertical bar with a slash through it, 16. That's a lot like the not equal sign, right? You just put a slash through the thing to say it's the negation of your thing. Okay, we're in a good place there. I wanna do 2 proofs and then 1 disproof. We're going to show something that seems reasonable but is in fact not true, using this divisibility definition. So, by the way, at this point you've got 4 definitions that you should commit to memory. Divisibility, the one we just looked at, to be a rational number, the definition of rational, but also we've got even and odd. There's 5th, prime. So we've got 5 definitions. Now, when we talk next week about the exam, I'll mention this again, but one thing I usually do at this stage, because you've got too many things to memorize, is let you have a half a sheet of paper for notes. I would strongly recommend your half a sheet of paper include writing all 5 of these definitions we've just been discussing down. All right, so Here's a theorem. For all AB in the integers, I'm going to specify it actually to positive integers. So if A is in the, well, let's write it differently. Let's just use an inequality for that. If A is bigger than 0 and B is bigger than 0, that implies, I think I want to parenthesize that. It's unnecessary, but it looks better, I think. But basically, A and B both being positive implies this, that if A divides into B, then A is smaller than B, or at least less than or equal. Yeah. I usually think of it as literally being smaller, but of course, a number divides itself, doesn't it? Ooh, that's a great example. I should have thought to do that. What would, if I just had any number as n and that same number as d, what's the witness for that? Okay, I think you were probably guessing it. 1? Did you guess 1? Yes. Okay, so if you've got one number that divides into another, the first guy is the smaller unless they happen to be equal. How can we prove that? Well, what do we get to suppose? Not much, honestly. We get to suppose that A and B are both positive. I'm going to say both if I've written R there, do I? Yeah, suppose A and B are positive integers. And then I'm trying to get to this statement. So now this statement is in another implication. So how do we prove an implication? You assume the if part, and you conclude the then part. Okay, fair enough. Then if A divides B, here's where we get to use the definition we just wrote down. If A divides B, there is an integer k. There is a witness for that divisibility question. Since A divides B, there is an integer k such that B is equal to AK. Now, I just want to ask you about the sign of K here. I'd rather not have to go into a big rigmarole to argue this. I think we can get away with just saying this. From this, isn't it clear that K has to be a positive number? Because if K were negative, A is positive, this side would be negative, and this side is positive. That doesn't make sense. So I always tell students, if you ever, while you're reading a proof, you come across something where somebody says clearly this thing is true, as if to be dismissive about it, that's actually the place to put your attention on, because it might be that the author of the proof is glossing over some important detail. But I really do believe this one is a place where saying clearly is reasonable. Clearly, K is greater than 0. Well, that's interesting because K is an integer and it's bigger than 0. Just collecting those two facts together, K is an integer and K is positive. It follows that K is greater or equal to 1. No, oh darn, I've erased the thing I wanted to have, but I've got k is greater or equal to 1. And I'd like to show that a is smaller than b. Or we're saying that a was the smaller number, it's the one that divides into the bigger number. So, you know what, just to keep it lined up the same way, let's write this as 1 is less than or equal to k. What am I going to do is multiply both sides of that inequality by a. What rule of algebra have I used here? If you multiply both sides of an inequality by the same thing, it changes the direction of the inequality if that thing is negative. But a is not negative, a is a positive number. That was our assumption. All right, so the direction of the inequality remains the same. Well, maybe I shouldn't put a period there, because what's AK? What's AK? It's B. So A is less than or equal to B. That was fun. Well, not really, but it's a detail that's nice to know. And if you've got that, you can actually use that proof to get some other things. That knowing that if you've got divisibility, you get an inequality is actually quite handy. So that's a good one to add to our stable of proofs. There is a nice property of the divisibility sign called transitivity. Did I spell that right? Transitivity, yeah. Which says this. It says if you've got 3 integers, if the first one divides the second, and the second one divides the third, can you guess what that's going to imply? A goes into B evenly, and B goes into C evenly. Well, A is going to go into C evenly. A divides C. That's probably intuitively appealing. I mean, it sort of makes sense, but even so, it's a statement requiring proof. So let's do it. You're going to suppose A, B, and C are integers, and the if part of this if then. A divides B and B divides C. Really ran out of space there, but I crowded it in. So we got that first sentence there. I'm going to have to move to the top of the board to write the rest of the proof, though. Where are we going to go next? We threw in our first suppose sentence, and notice it involves this concept of divisibility that we have just written down a formal definition for. So let's use that. That second sentence begins with the word since. Since A divides B, there is an integer k such that the big one is equal to k times the little one. B equals is AK, or KA, I don't care. Right. And then also we've got B divides C. This is going to be essentially the same sentence. No, I'm not. Did I really do that? Yeah, you guys know this mistake already, so I'm just being silly at this point. We know you can't use K again. What should we use? How about, I don't know, Q? So now the big one is C, and it'll be equal to Q times B. Now, these two things here are kind of your ingredients. B is equal to Ka, and C is equal to QB. But what you want is to find something so that C looks like a number times A. How can we use these pieces of algebra to get us that C looks like something times A? It's literally substitution. You see, that symbol B and that symbol B are both equal to Ka. So you can stick this Ka here, this guy, right in where that is. I've just uglified my nice proof by writing all this junk on it. Let's take all that away. Let's make it look like we didn't have to have that discussion. Yeah. Mostly repaired. Okay, so what we're going to do is make a substitution. C is equal to Q, let me write it a second time, QB, so it's equal to Q times Ka. I'm just replacing the B with what we know it's equal to. Oh, that's a bad sound. Didn't know it did that. All right, fine. But I want it to look like C is a number times A. Okay, great. Just reparenthesize that. Do QK times A. That's the associative law. That's valid. So since QK is an integer, it follows that that C is divisible by A. Or that A divides evenly into C, which is what we were after. So we can fill in our rectangle at the end of this. All right, I promised one last thing in this section, which is to look at a statement that seems plausible but turns out to not be true, and try to figure out how we could, generally speaking, come up with understanding why something that seems plausible would not be true. So, here's the statement. For all A, B, and C in the integers, if A divides into the product of B and C, then it divides into one or the other. That seems to make sense. Let's try some examples. Suppose I had 2 divides into 3 times 4. Because that's 12, right? And 2 certainly divides 12. They're both even numbers. So, I mean, 2 divides into any even number. So that's true. And of course, 2 divides 3. That's false, but it's okay because 2 divides 4 is true. So we've got the 2 divides into the product, and not this one, but the second one is true. And if one of the pieces around an or sentence is true, then the whole thing is true. Seems good so far, but it's actually not a true sentence, so this example didn't seem to point that up. You want to try something else? Trying to think of a good example. 54. 54 is divisible by 3. You can tell because 5 and 4 is 9 and 3 divides 9. Right? Wow, this is interesting. So that for all A, B, and C, I could think of any of the ways that we can divide 54 up as a product. Like, wow, what would they be? Factors of 54. We could have 2 and 27, or 3 and 18, or 6 and 9. And I think that's it, because the rest of them are the same things in reverse, 9 and 6, and 18 and 3. Okay, so, well, I guess I'll finish writing them out, 27 and 2. The question now is, having divided 54 up into a product in all possible ways, is it always true that one of them is divisible by 3? 27 is, 2 is not. Oh, here both of them are. That makes the or sentence even more true. Here they both are. But in every case, at least one of the factors is divisible by 3, so it works. 3 divides 2 is not the case. I'm going to, instead of writing that little X there, I'm actually going to use the official notation, put a slash through the symbol. But it does divide 18, for instance. So this guy's true. That was not, but the or sentence is. Yeah, put them together. So why does this fail? Well, I was sort of cheating and giving you examples where I knew it was going to fail. These guys are both prime numbers. And this sentence becomes true if you assume A is a prime number. But if A is not a prime number, then you can come up with examples where it doesn't work. So let me show you a counter example as opposed to an example. Suppose A was 6. A is 2 times 3. It factors. You can make B be something that picks up the 2, but not the 3, and C be something that picks up the 3, but not the 2. So, for example, you could have B be 10. That's 2 times 5. It's cool. It doesn't have any 3 in it, though. And C could be 3 times something, about 21. Right, 3 divides 21, sure it goes in 7 times. But 3 certainly doesn't divide 10. What am I going for? Oh, and 2 doesn't divide this one, right? So this one is divisible by 2, this one's divisible by 3, but not vice versa. Yeah. So using those A, B, and C's, we've got 6 divides 210. Okay, maybe that's not completely obvious, but notice the digits add up to 3. So it's divisible by 3, and the last digit is 0, so it's even. It's even and it's divisible by 3, it's divisible by 6. 6 divides 210, but 6, does it divide 10? No, it does not. And does 6 divide 21? Nuh-uh. So neither A divides B nor A divides C are true in this scenario. Now, that was a little bit of a stretch. There's a much easier answer to this. If you know the number of factors, then use B as one factor and C as the other factor. Just to save a little board time. Another counterexample would be A equals 35, B equals 5, and C equals 7. You recognize the factors of 35, right? Certainly 35 doesn't go into 5, and it doesn't go into 7 because it's bigger than them. And if it divided them, it would be less than or equal to them, by our first theorem we proved. But it certainly does divide their product because A divides BC is really 35 divides 35. And like we said before, a witness for that is the number 1. Okay, so great. That's the last bit of stuff we're going to do in section 4.4, and that's also the last bit of stuff that will be responsible for our test next week on Thursday. So we'll be doing a worksheet on this stuff tomorrow, and well, tomorrow for you. And we will be reviewing a sample test on Tuesday next week and then taking the exam on Thursday next week. If you have not got a webcam or have not yet downloaded WebEx or something like that to your cell phone, take care of that, because you're going to need to, for proctoring purposes, you're going to need to keep a webcam aimed at yourself. It's fine if it's on your cell phone. That'll be a little trickier because it's harder to hold a cell phone in the right spot, but Scotch tape works great. Anyway, see you tomorrow, and this will be fun.